Welcome, this is Brett Sanders, and this video provides an introduction to using Primo. I have a desktop set up here with a Finder window. I've got a terminal window, and I've got a Matlab command window set up. And you'll notice that the Finder window I've called it PRIMo-GPU demo, and inside of it I have a zip file which contains the Primo GPU code and sample input files and Matlab scripts. I grabbed this code by downloading it off of GitHub, but sometimes we may just pass this zip file to users and share it that way as well. So if you have this zip file, you can double click it and it'll create a directory with all of the Primo input files. I think it's sort of useful just to kind of shorten this, keep your directory a little bit more tidy. Inside of this folder, there is a directory for binaries, so when Primo is compiled, the executable will sit in here. The source code for Primo sits in this src directory, and it's just a fortran 90 text file. And then there is a single project file set up with many different input files that can be used by Primo. We'll get to that in a little bit. In the main directory, there's many different Matlab files, and those include scripts for pre-processing, post-processing, and additional function files that are used by those main pre and post-processing files. So one thing we can do to get started is to create a binary executable. So in order to do that, you want to have a Fortran compiler installed on your computer. I have gfortran installed here, so I'm going to be using that compiler. To run this on a GPU, you need to use a compiler with that's configured to provide instructions to the GPU. And so typically the gfortran compiler is used, and that compiler is typically available on computing systems, but not necessarily on your home machine, your local machine. But to compile Primo, we can just use the gfortran command. We're going to create an executable within the binary directory, so we'll call that PRIMo-GPU, and the source code is in source PRIMo-GPU.f90, and it didn't find the file. So that's because we aren't in the right directory. So we're going to go down one directory, PRIMo-GPU 2.0. Now we'll do the same command as before. Just put the up arrow. It brought me back to these previous commands. So you run the compiler and it ran. I do get a warning message. I've been getting this warning message for a while, but the binary was created. So if we type ls bin, you can see that the Primo GPU was created, and you can see that was created just now. So now we have an executable set up and ready to go. The next thing we want to do is create a set of input files, and inside of the Miami Gate files there are many basic input files, and most notably there's this main input file called input. So I open that with a text editor, and inside there are a number of different controls over simulations. The upscale factor is a big one, but perhaps most notably here is that this line here shows that there's a stopping time for the simulation and a time interval for saving output. That's set for 3600 seconds and 360 seconds respectively. So that means that the model will simulate 1 hour of flooding, and it will export output, every, um, let's see, 6 minutes. So what Primo needs to run is typically a digital elevation model, and a land cover model, and that land cover model is used to inform things like manning resistance parameters. So for this basic setup, this test case Miami Gate, I already have a script file inside of this directory called primoprep Miami Gate. And this primoprep Miami Gate script file will go into the Miami Gate folder. Inside that folder, it will find open this up a little bit. It will find a TIFF file, which contains the digital elevation model for the site. And it will also find a land cover file for the site. Both of these are raster files saved at the same resolution with the same spatial extent. Okay, and then those files are input, and then the model will generate a set of binary formatted input files that Primo will load in order to run a simulation. So all this is set up to be able to just run this. We're going to get into the folder. And what this did is it created a spatial domain here that's masked with some boundary areas masked out. This is the Miami River, and this is another channel that branches off the Miami River. And it's a relatively small test case that can be run on a local machine. You don't need to use a supercomputer or GPU to run this. And for a basic test case, what happens is that we just apply a high rainfall rate and watch the water pond in the simulation. So that's basically what happens. This script file can be closed for now. The first figure shows both the digital elevation model and the land use data that was input. So you can see those two basic inputs that came into Primo. So I'll close that. You'll notice that inside the Miami Gate directory, what's happened is that this Matlab script created a number of input files that can be used by Primo. One is we call our Z file, which has the ground elevation data. We have a land cover file, which has a land cover classification for each pixel. We have a mask, which tells the model which cells are active and which cells are not active. And we have a number of seepage parameters related to the seepage functionality of Primo. And that's not required for all simulations, but if you turn on the seepage option, then those input files will be needed, and they'll need to be parameterized. And the code to kind of set up those files is all sort of embedded within this primoprep file. Great. So now we've created the input files for Primo. We'll go back to the main input file. I just want to note that there are a number of options in Primo. Options for boundaries, options for point sources, options for precipitation, options for have a levee grid classification, options for adding storm drains, options for adding monitoring stations, options for doing a dam break study, options for having gates in your model, options for resolving seepage, and this options for stability, which adds just a little bit of stability to the model. And as of now, you notice that most of these options are set to 0, which means they're turned off. I have the option stability turned on, so that gives it just a little bit more stability, and that tends to be something I keep on all the time. And for this particular simulation, the one thing that is turned on is the precipitation. So in this case, 0 means that precipitation should be a constant, and I'm specifying it to be 100 millimeters of precipitation every 60 minutes. So that's 100 millimeters per 60 minutes, or say 10 centimeters an hour. So this first simulation, it's going to be configured with an forcing from rainfall. Up here are the boundary conditions that will be enforced by the model. And we have a boundary condition for the left, for the right side, for the bottom side and for the top side, and all those are set to 1, and 1 corresponds to a wall. So that's kind of the most stable, basic boundary condition. So with that input set, we can go down to the command window, and we're just going to run Primo, and we'll do that by saying period / bin PRIMo-GPU, and then we tell it the name of the test problem that we want to run. And it didn't run, which maybe is a good thing, because the mistake is that you'll notice that I wrote in Miami test, but the name of this test problem is Miami gate. So that's why we got an error. So I'll try this again. Okay, so it's started Primo, it read the input files, making an upscale grid, it sets the initial conditions, and then the model runs. And as it runs, it writes output to a log file, and that log file can be found here. You'll notice that that file is will grow over time as the model runs, and inside of it, if you were to open that file, what you'll see is, a report of the time step that's being used, the cumulative time of the model, and when the model finishes, and the model just finished, you'll get a report on sort of the mass conservation properties of the model. So this number here is a residual that is an overall mass balance to make sure that the model didn't somehow lose some water. And in this case, the residual is 10 to the minus 6, which is excellent. The initial volume in the system was 0. When the model ended, you can see this is the volume of water in the system. Sometimes cells will take on a negative depth for stability purposes, and so that's not ideal, but it's not fatal either. But we try to monitor that number and make sure it's a small number compared to the volume of water in the model at the end. You get a report on how much water came in as precipitation, how much water infiltrated. It looks like the seepage must be turned on, and then the amount of water that came from sources and drains in boundaries and the volume seep. So this may not mean it's turned on. I'll have to come back to that. So the model ran. You'll also notice that because we wanted to export data every 360 seconds, there are output files in this raster folder for different time levels. So the initial time level is a 0000, then after 360 seconds, the next time level is 0001, and so on. And so there are 10 different time levels saved. Different variables are saved. So eta is the surface water elevation on the coarse grid. HD is a downscaled fine resolution flood depth. And then we also have x velocities, which is u, and that's on the coarse grid. And we have v velocity v, and that's on the coarse grid. And then we have this volume variable, which is an average depth on the coarse grid, and that's also saved. So those are the main outputs that get saved by the model. So 10 different times levels are saved. And then there is a post-processing script called primoviz, which is configured to upload that data. So we'll click that file. And over here, we kind of move along. This is the primoviz for Miami gate. And we tell it that there were 10 time levels that were saved. The interval between the saves was 360 seconds. And then there's some options to either visualize the downscaled flood depth data or visualize the value of eta, u, and v on the coarse grid. When those visualizations are done, you can choose to animate them here. So the animate flooding right now is turned on. And if you want to save those animations like as an MP4 file or a GIF file, you can turn this to 1, just like that, and then the saving will be done. But for now, why don't we go ahead and just run that script, and it will create a little animation of the fine scale flood depth, And then also, this is a three-dimensional view of the coarse grid data where the surface corresponds to the variable eta, which is how high either the ground is or the water is above some datum. And the coloring is proportional to flood depth, which is based on the volume variable that's output. So that is a full run through of Primo functionality, from grabbing the initial zip file. So we started with just grabbing zip file, extracting that, renaming it. We went and compiled the Primo code in the directory, and we also ran the Primo model with this command. I'm just using the up arrow to cycle through previous commands. You can see what we did. One error that comes up quite a bit on Macs, and I thought I would mention to people, is sometimes when the compiler command is run, like this one, let's go back. Where was our compile? So the gfortran command. Sometimes you'll get an error message that has to do with some conflict with running Anaconda on your computer. So if that error comes up, the way to fix it is just to say conda deactivate. And that command will then turn off the Anaconda functionality that is interfering with the Fortran compiler. And you'll turn that on, and off you go, and that compiler will once again run. And you will, as I said before, I get this error message, which doesn't seem to be, it's annoying, but it doesn't seem to be a problem. It's still, the Fortran compiler still works. Well, I'm going to stop there, and hopefully this is a good way for you to get started on Primo.